So, topic for today will be sequences, and I hope you have watched the lecture from last time. So we'll just continue or we'll just proceed with the examples that I have prepared in here. So basically, a sequence is just a function which maps the set of natural numbers, including zero, to a set of real numbers. Okay, so um, let's start. So in here, we want to find the formula for the general term an of the sequence, assuming that the pattern of the first few terms continues. Okay, so we have here first item, we have the set which contains in order -3, 2, -4 over 3, 8 over 9, -16 over 27, and then dot dot dot. So when we had the lecture, you were actually given three specific examples of sequences. One of them is the arithmetic sequence. The other one is the geometric sequence. The other one is the Fibonacci sequence. So in this particular um, set or particular sequence, you can try each of them, and you will see, or at least you will be able to observe that this sequence here follows a geometric sequence. Okay, so in that sense, let us try to find the formula for this geometric sequence. So we start with our a sub 1. We start with our a sub 1, which is equal to -3. A sub 2, this is equal to +2. A sub 3, this is equal to -4 over 3, etc. Okay? So again, our guess here is actually that this sequence is a geometric sequence. So we will try to find the common ratio, okay? The common ratio, and of course the initial term. The initial term is already given to be -3, okay? So how do we get the common ratio? So we have R, which is equal to a sub 2 over a sub 1, and we say it's common. It should mean that every ratio which follows uh, something like this, they should be all equal to each other. So you have your a sub 3 over a sub 2. This must be equal to a sub 4 over a sub 3, and in the end this should be equal to something like a sub n over a sub n minus 1, where n is greater than or equal to 2. Okay, and we see that, yeah, if we get the ratio 2 over -3, and then the other one -4 over 3 over +2. Then if you look at the next terms here, 8 over 9 over -4 over 3, they will have the same values. And therefore, we confirm that this sequence here is a geometric sequence. Okay? So let me get this space here from the second item. Anyway, the second item we will see, we will easily get a formula for this sequence in here. So anyway, we have a sub 2 over a sub 1. It's what? We have 2 over -3. So we have -2 over 3. And then we verify that this is the same as a sub 3 over a sub 2. A sub 3 over a sub 2, we have -4 over 3 divided by 2. So if we calculate this, you will get negative 4 over 3 times 1 half. And therefore, this is indeed negative 2 over 3. And then we verify further. We have a sub 4 over a sub 3. And our fourth term here, it's 8 over 9. So you have 8 over 9 all over the third term here, it's negative 4 over 3. So negative 4 over 3. And then this is 8 over 9 times negative 3 over 4. And therefore, we easily see that this is negative 2 over 3. So what I'm saying is, indeed, if the next terms follow the pattern that is given or that is implied by these first few terms here, then the ratio a sub n over a sub n minus 1 will be negative 2 over 3. And therefore we have what? An here, this is equal to a sub 1 r to the n. That's the formula for our geometric sequence. And what? A sub 1, that's equal to negative 3. Okay? And then our r, it's negative 2/3. Okay? And then you have, by the way, since we are starting here with a sub 1, okay? We are starting here with a sub 1. Our exponent here will be raised to n minus 1. So this will be raised to n minus 1. And as you can see, when n equals 1, we have 1 minus 1, that's 0, so we will get negative 3. When n is equal to 2, you have 2 minus 1, that's 1, so you will get negative 3 times negative 2/3, and therefore you will get positive 2. Okay? And so on and so forth. Okay? So this is the formula for our an. So indeed, this is a geometric sequence. Okay? Now, for this sequence here, you have 1, 0, negative 1, 0, 1, 0, negative 1, 0, etc., etc. So, for this sequence, you expect that what? This is something cosine or sine function, because if you try to graph it in the uh, Cartesian plane, what you will actually get is something here, and then something here, and then something here, and then something here. And then the terms bounce from this from one of the points going to the next point, right? So negative, so positive 1, 0, negative 1, 0, positive 1, etc. Okay? So you expect that this must be sinusoidal, okay? This must be sinusoidal. And one way to consider is that this sequence is given by the formula cosine n pi over 2. And your n here starts from 0. Okay, 0, 1, 2, etc. So when n equals 0, you have cosine 0, that's 1. When n equals 1, you have pi over 2 here, so cosine pi over 2, that's 0. When n equals 2, you have 2 pi over 2, that's cosine of pi now, which is negative 1. And then you continue with your n, and you will end up with this expression, or this sequence. Okay? So, this is one way. This is one way to write this sequence here. Another way to write the sequence is, of course, in terms of sine. So you can actually write this in terms of sine, but the argument inside the sine function will be what? N plus 1 pi over 2. And in this argument, you start your n with 0, 1, 2, etc. Because when n equals 0, you have sine pi over 2, that's 1. When n equals 1, you have sine of 2 pi over 2, sine pi, that's 0. N equals 2, you have sine of 3 pi over 2, that's negative 1, and so on and so forth. Okay? Or maybe if you want to start with n equals 1 as your first term, then you just adjust this n here or this n here. Okay? So those are some ways to write this sequence here. Okay? So for this example, or for this set of examples, um, we are given how to convert these first few terms of a sequence into some formula. Okay? And then there will be some exercises where you are given the formula and you will be asked to write the the terms of the sequence. But that one is easier in a sense that you just plug in the value of n, and therefore you will be able to obtain the first few terms or the nth term, etc. So I will not include that in the examples. Now, given our given our sequence, what our goal is actually finding whether the sequence is convergent or divergent. Okay, and in order to find the convergence or divergence of the sequence, we actually find the limit. Okay, if we get a limit that is a real number, then we say that the sequence is convergent. And otherwise, if we don't get a limit, okay, or the limit is plus or minus infinity, then we say that the sequence is divergent. Okay, and since we are just trying to find limits of sequences, then we use all the techniques that we know from or that we have learned from Math 21. Okay, if possible. Okay, so for example, in here, we want to find the limit of an as n approaches infinity. Okay, so let us write this. Limit as n approaches infinity of 3 plus 5n squared over n plus n squared. So in here you have a polynomial over polynomial. Okay, so one technique that we use in here, or one technique that we use in order to find the limit as n approaches infinity, is to multiply and divide. Okay, multiply and divide both the numerator and the denominator by 1 over the variable raised to the highest power that appears in either the numerator or denominator. Okay, so what I'm saying is, in the numerator, this is degree 2 polynomial. In the denominator, this is also degree 2 polynomial. So the highest power of the variable n is 2. So we multiply and divide both the numerator and denominator by 1 over n squared. Okay, 1 over n squared. And then if we simplify this, so limit as n approaches infinity, we will get 3 over n squared plus 5 divided by, in here, 1 over n plus 1. Correct? So if we distribute this 1 over n squared, okay, in the numerator and then here also in the denominator, these are the things, or these are the expressions that we will get. And therefore, as n approaches infinity, we know that this guy here, this will go to 0, and this guy here will also go to 0. Okay? And therefore, we will actually get 5 here. This means that this sequence here is convergent. So therefore, let's just write the conclusion. Therefore, AN is convergent. Okay? Next question here. So we have the sequence AN equals n to the 4 over n cubed minus 2n. Okay? Now, the technique that we used here, okay, the technique that we use here is to multiply both the numerator and denominator by 1 over the highest degree that appears in either location. So in here, what we're going to do is to use the theorem that we know with regards to polynomial over polynomials. Okay? So in this case, we say that the degree of the numerator is bigger than the degree of the denominator. The degree of the denominator I hope you remember this theorem. Okay, therefore the limit of that an as n approaches infinity, this is also infinity. And I'm writing plus infinity because the sign of your n to the 4 here is positive. So it will only go to plus infinity. Okay? So this solution here, this is a valid solution. Okay? You can use this when answering problems. Okay? Because you are only applying a theorem that you already know. So this is a valid solution. Okay? And since we are here, what are the other counterparts? Okay? If the degree of the numerator is the same as the degree of the denominator, then the limit of the sequence as n approaches infinity will be the ratio of the leading coefficients, right? Just like in this example, we have both degree 2. The leading coefficient in the numerator is 5. The leading coefficient of the denominator is 1. So 5 over 1, you only get 5. And also, if the degree of the numerator is less than the degree of the denominator, then the limit will be equal to 0. Correct? So if we have a polynomial over polynomial, you can use that theorem. And what does this mean? We have a limit of an as n approaches infinity to be plus infinity. This means that your sequence an is divergent. Okay? Next question here. Determine whether the sequence converges or diverges. Find the limit if it converges. We have here a sub n equals 3 to the n over 7 raised to negative n. Now, we use loss of exponent here. This is just what? 3 to the n times 7 to the n. And this is actually equal to 21 raised to n. And without doubt, this is exponential with base greater than 1. So definitely, the limit of your an, this will also go to plus infinity. And therefore, this sequence here is divergent. Is divergent. Okay? Next problem here. So we have a sub n equals e to the minus n or minus 1 over square root of n. Okay? So here we have the limit. Okay? We have the limit as of an as n approaches infinity. Okay? Approaches infinity. This one is the same as the limit as x approaches infinity, e raised to negative 1 over square root of x. Correct? And then, the reason why I am writing it this way is because I want to put the limit in the exponent. This is equal to the limit, e to the limit as x approaches infinity of negative 1 over square root of x. Okay? And we know that this guy here, you have what? As x approaches plus infinity, 1 over square root of x, that will go to 0. And even if you have the negative, that's just 0, which means that this is equal to e to the 0, and this is equal to 1. Okay? And therefore, an is convergent. The sequence an is convergent. Okay? Now, you might be asking, why did we have to do this part here? Okay? When we replace this variable from the index n to the variable x, we are assuming that this becomes a continuous function, or at least we are talking about a function whose domain, okay, whose domain is a subset of of well, the domain will always be a subset of the set of real numbers, but the domain will contain all real numbers except those numbers that will make the denominator does not exist, or make the denominator 0 if it's a rational function or so. Okay? And take note that you can only do this, okay, when you have a continuous function. Okay? Remember, one of the conditions for you to be able to put the limit from here into the composition is that the function must be continuous. Okay? So that's the reason we do this. Okay? So you have to recall those little details from your Math 21. You cannot just put this up there without talking about continuity. Okay? So that's the reason why I have to change from sequence to a more continuous function. Of course, this function is discontinuous. Well, actually, this function is continuous from 0 to plus infinity, not including 0. We don't also allow negative numbers here. Okay? So what I'm saying is in here our x is from this interval. Okay? And this function here is continuous on this interval. That's why we can apply this guy here. So those are some little details that I want you to remember. Okay, so do not just apply theorems and concepts and you are not checking the hypothesis. Okay, next problem here. So we have the sequence an equals square root of 1 plus 4n squared over 1 plus n squared. So the same as in the previous example, not really the previous slide, but a previous example. So what we can do here, okay, so limit as n approaches infinity of an, this is equal to the limit as n approaches infinity. Then let me write this big radical here. You have 1 plus 4n squared divided by 1 plus n squared. And then we multiply this since they have the same degree. Okay, they have the same degree. We can just multiply and divide this by 1 over n squared because the degree is equal to 2. Okay, so same technique as in before. So in here you will have the limit as n approaches infinity of square root of, you have 1 over n squared plus 4, and then here divided by 1 over n squared plus 1. Okay, and just like in the previous problem here, you may put this limit inside that radical. Okay, you may put this limit inside that radical, but you have to remember that you must be using some continuous function in order to do that. But we will not do that here. Okay, so as n approaches infinity, this 1 over n squared here, it will just go to 0. And same with this guy here, which means that as n approaches infinity, this will go to 0, this will also go to 0, okay? And therefore, we'll just get square root of 4 over 1, or this is equal to 2, okay? And again, just write the conclusion, therefore, the sequence is convergent, okay? Next problem here. So determine whether the sequence converges or diverges. If it converges, find the limit. So in here, this is factorial, which means definitely we cannot apply any techniques for functions, for continuous functions to be more precise. Okay. So what we're going to do is just to study these numbers here and recall the definition of factorial. So I hope you still remember that definition of factorial. Okay. So in here you have 2n minus 1, 2n minus 1 factorial divided by 2n plus 1 factorial. And then in here, we just look at the denominator and remember the definition of factorial. So in the numerator, we still have 2n minus 1 factorial. For the denominator, you can rewrite this as 2n plus 1 times n times 2n minus 1 factorial. Okay? So that's from the definition. So let me just recall it here. You have your n factorial. This is n times n minus 1 times n minus 2 until you have times 2 times 1. Okay? So consecutive numbers starting from n going down to 1, you multiply all of them. Okay? So in here, this is your 2n plus 1. The next lower number will be 2n plus 1 minus 1. Sorry, this must be 2n. This guy here must be 2n. Okay? And then the next number after 2n, the next lower number before 2n, you have 2n minus 1. The next number lower than 2n minus 1, it's 2n minus 1 minus 1, which is 2n minus 2. But we will stop enumerating them because in here we already have 2n minus 1 factorial, and in here we have the 2n minus 1 factorial in the numerator, which means that this guy here will be simplified into 1 over 2n times 2n plus 1. Okay? And therefore, we get the limit. We get the limit as n approaches infinity of a sub n. This is equal to the limit as n approaches infinity of 1 over 2n times 2n plus 1. And we easily see that this is equal to 0. And therefore, this sequence here is convergent. Okay? Next, we have our an equals ln of 2n squared plus 1 minus ln of n squared plus 1. So for this sequence, we use properties of logarithm. Okay? We have ln of something minus ln of another thing. You can rewrite this as ln of the ratio 2n squared plus 1 divided by n squared plus 1. Okay? And then the same thing, the same solution as in before. You can have this written as you have your 2n squared plus 1 divided by n squared plus 1 times 1 over n squared over 1 over n squared. Okay? And this is equal to ln of 2 plus 1 over n 1 over n squared divided by 1 plus 1 over n squared. Okay? Then again, those little details, if you want to get the limit of a sub n, which is equal to this, you can put the limit inside the parentheses assuming that you have a continuous function. Okay? So try to recall that. But in here, we can skip that part. So limit as n approaches infinity of a sub n. This is equal to the limit as n approaches infinity. So we write this final form here. Ln of 2 plus 1 over n squared over 1 plus 1 over n squared. And as usual, as n approaches infinity, this will go to 0. This guy here will go to 0, which means the limit will just be ln of 2. And therefore, this sequence here is convergent. Okay? So for this example, we have the sequence n squared e to the minus n. Okay? So our an, this is n squared e to the minus n. And this one is equal to n squared over e to the n. Okay? So in this particular example, you will learn that the exponential function grows faster than the polynomial function. Okay? In fact, whatever polynomial you put in the numerator or whatever, okay, when you compare it to exponential function, the exponential function will always be faster. Okay? Whether your degree for the polynomial it's 100, 1000, 1 million, etc. Your exponential will still grow faster. Okay? And I hope that it was emphasized when you were working on limits back in Math 21. But anyway, so in here, we get the limit of this an. Let's say we let f of x be the function x squared over e to the x. Okay? And we say that, well, this is continuous everywhere, so I'll not put the domain. Okay? Then, here, you want to find the limit of an, limit of an as n approaches plus infinity. And this is the same as the limit as x approaches plus infinity of f of x. And this is equal to the limit as x approaches plus infinity of x squared over e to the x. And then, you know, this is infinity over infinity. Okay? So you apply Lopital's rule. So that's the reason why I have to introduce the function, because I'll be using Lopital's rule. So this is limit as x approaches plus infinity. You have your 2x in the numerator. In the denominator, you still have e to the x. And this is still infinity over infinity. So we apply again L'Hopital's rule. And this is equal to the limit as x approaches plus infinity of 2 over e to the x. And this one is not indeterminate form. And we have here 2 over infinity as x approaches infinity, which means that this is equal to 0. Okay? And therefore, this sequence here is convergent. Okay? So you see the difference between the techniques I am using. The necessity of continuity here. Okay? We used Lopital's rule, meaning we will be using or we have used derivatives, and therefore when talking about derivatives, continuity must be present. Okay? And then I think this is my final example for this discussion. We want to find the limit a sub n equals arctan of ln of n. Okay? So in here, you have to remember if you consider the continuous function f of x equals arctan x. Okay? So let me just draw that one. So for the arctan x, this is your pi over 2. This is your negative pi over 2. And then your arctan x is something like this, going to that pi over 2, and then something like this. Correct? And we know that the behavior of arctan x, as x approaches infinity, the graph will approach y equals pi over 2. So recalling that, the limit as n approaches infinity of a sub n, okay, so limit of arctan, so as n approaches infinity of arctan of ln of n, this is just pi over 2, because ln of n as n approaches infinity will go to plus infinity. So arctan going to plus infinity will be pi over 2. Okay? So that's my last example. Thank you for watching. Bye-bye.